So good afternoon, everyone. I'll be talking about an ongoing work in collaboration with Ankush, who is a PhD student, Professor Subhro Bhattacharjee, and Professor Vijay Chennai from IISc. So I'll be talking about a system where the low energy theory is described in terms of Dirac fermions. And these Dirac fermions have a microscopic origin, which involves spin orbit coupling mechanism. And this specific model is defined on a honeycomb lattice. So before going on to the details of the model, so some words of motivation. So we know that spin orbit coupling is kind of essential in realizing topological phases of matter. And in presence of Coulomb interactions, it can give rise to even richer phase diagrams. So this schematic phase diagram taken from this article nicely shows different possibilities of phases that can appear in presence of spin orbit coupling and Coulomb interactions. And in many of these phases, symmetry, and especially the implementation of symmetries on low energy degrees of freedom, plays a very crucial role. And I mean, given a system and its symmetries, it really depends what are the low energy degrees of freedom and how are the symmetries that implemented on the degrees of freedom. And it can have non-trivial consequences on what are the different phases that can be realized. I'll be demonstrating in the specific model that we'll be talking about this specifically 2 points, that how the spin orbit coupling interactions and different symmetry implementations give rise to new phases. This is the outline. So first I'll be talking about what the low energy degrees of freedom and how the symmetry is implemented. And second, how different what are the different interaction driven phases, mainly symmetry broken phases. Okay, so the details of the model is the following. So the model is defined on a honeycomb lattice. And on each side of the honeycomb lattice, there are 4 states. And you can write some hopping model using on that lattice. So psi is a 4-component annihilation operator. And this is a Coulomb interaction term. So this model was introduced in this article by Yoshikawa and co-authors as an effective model of this kind of materials. Where the structure is lattice structure is a quasi 2D structure, and there's the structure is made out of corner sharing octahedra, and if you join the central atoms of the octahedra, you get this honeycomb lattice, and this central atoms has 1 electron in its last outer orbital, and the outer orbital is d. So this is d1, and because of spin degeneracy, this is 10-fold degenerate. Now, because of this octahedral structure and crystal field, this degeneracy splits, and it turns out that the low energy degrees of freedom is a 4-dimensional Hilbert space at each side. So that's why at each side there is a 4-dimensional Hilbert space. And this author showed that the minimal model that you can write down for this kind of materials is kind of this, where there is a hidden kind of SU4 symmetry, which is not apparent. So U is a 4x4 unitary matrix, and this is a Coulomb interaction term. So if I write down, if I determine the band structure in a non-interacting limit, putting the Coulomb interaction to 0, I get this kind of a band structure where there are 4 bands, and each band is 4-fold degenerate. The degeneracy is expected because of the SU4 symmetry that is there in the model. Now, going back here, so at each side there are 4 states and 1 electron. So the system is at 1/4 filling. So this lower band is fully filled. And this conduction band and lower valence band touches each other at 2 points. So this is very similar to the theory of graphene with electrons, normally spinless electrons. So the theory, low energy theory, continuum theory, is described by Dirac fermions in 2+1D. This gamma mu are Dirac matrices in 2+1 dimensions. And this identity matrix here really tells that there are these bands are 4-4 degenerate. So there are 4 copies of Dirac fermions, let's say. 4 copies of the same Dirac fermions. So for future reference, I'll show you many matrices of this form of direct product form. So the first matrix will be written in the flavor space, which tells you, how different degenerate bands mix with each other, which is in this case identity. And the second matrix will, you can think of it kind of acting on the Dirac cone space or valley space, mixing the 2 valleys and bands. Okay, so having derived this low energy theory and the low energy degree of freedom, the next question is the following: that how these different degrees of freedom transform, And given the symmetry transformation, what are the different phases that are driven by this interaction? Right. So coming to the symmetries, let's say, so first of all is lattice symmetries, the translations and the rotations of the honeycomb lattice that we have. So this chi, which is a spinor, which describes the Dirac fermions, transforms linearly under this symmetries, and this matrix is important. So this matrix has a direct product form, which first is a flavor space, acts on the flavor space, and the second acts on the, let's say, valley space. And it's important that this flavor space matrix in this case is non-identity. So if you compare it with graphene, graphene honeycomb lattice with spins, right, normal spins, this flavor space matrix will be identity because rotations and translations, it doesn't change the flavor. Spin up remains spin up. But in this case, because of the degrees of freedom of spin orbit coupled, this is not identity. For example, this inversion which is a symmetry of this lattice, and I have some non-trivial matrix, non-identity, which is not identity. Similarly, there is a time reversal system in the time reversal symmetry in the system, which is implemented. And most importantly, there is an emergent SU8 symmetry in the system, which is, so as I said, there is a SU4 symmetry, which is really microscopic. But this SU8 is emergent. When you go to the low energy continuum limit, this symmetry emerges. And the generators of this symmetry are the following. So these are the SU4 generators, which are even present in the microscopic model. Then there are this chi, which form a SU2, which can be thought of as a rotation between the valleys, SU2 rotation between the valleys. And then if you combine this, you can generalize this and form a SU2 group. So basically SU4 and SU2, combined together form this emergent SU8 symmetry. So once we have all the symmetries, now we ask and we know how the symmetry acts on the low energy degrees of freedom. We ask what are the different phases that are possible. So this, without any interaction, it has a Dirac cons, like the semi-metal kind of behavior. And you can show that in presence of weak interactions, this term is irrelevant. So this semi-metal phase is really stable in presence of weak interactions. But in presence of strong interactions, what can happen is that this kind of a fermion bilinear can get an expectation value. So think of some Howard stratonovic transformation, doing some mean field theory on this interaction. So then we ask the following question: that what are the phases that can be obtained by condensing this fermion bilinears like this? And it turns out that the fermion bilinears, which are this form, where PA is a symmetry generator of SU8, are the most important fermion bilinears because these are the slowest decaying. So if you want to characterize some symmetry broken phase, you want to look at these operators. These bilinears. So there are 64 of such bilinears, and now we basically want to treat this as order parameters and see how this transform under with different symmetries. Okay. So we turn on to ask the question that how these 64 bilinears transform under, let's say, lattice symmetries. So lattice symmetry, so it turns out that this lattice symmetry, the space group of the lattice, has 1, 2, and 3 dimensional representations. And this 64 bilinears, which transform under each other under lattice symmetries, form a 64-dimensional representation, which is of course reducible. And this reduces like this. So there are 6 one-dimensional representations, 5 two-dimensional, and 16 three-dimensional representations, which can be further classified using time reversal symmetry. So E and O implies time reversal even or odd. Okay, so once we have classified the 64 bilinears, right, using the lattice symmetries, we go to each representation and ask what kind of phase is this, looking at how it breaks the microscopic SU4 and lattice symmetries. So I'll show some few examples. For example, there are four bilinears which are invariant under the microscopic SU4, which is, I call flavor SU4. So the first of the bilinear, which I write as chi bar chi, is really a quantum Hall mass in the sense that it is odd under time reversal, it's odd under parity. And if you couple it to a U1 gauge field, like electromagnetic gauge field, and integrate out the fermions, let's say, you can have a Chern-Simons in your action. So it really tells that if you have an edge, there will be edge mode. So this is really a quantum Hall mass. And this NF equals to 4 here, it tells you that there are 4 copies of, let's say, your flavor, the 4 times the quanta of conductivity is the coefficient. And the second, and the rest 3 bilinears, which are again symmetric under SU4, form another phase, which is a density wave and has a stripy order. And these 3 bilinears correspond to the 3 stripy patterns on the honeycomb lattice. So this can be, I mean, at this point, I would like to compare with the theory of graphene. So similar analysis can be done for graphene as well, where you have honeycomb lattice and spinful electrons, normal spins. Right? In that case, the symmetries implementations are different, as I pointed out. Under rotation, the spins won't change. So in this case, it turns out that, I mean, which was worked out here, that there are again 4 bilinears which are invariant under spin rotations. And one of the bilinear gives rise to this quantum Hall phase. One of the bilinears gives rise to a staggered charge density wave, where the charge densities on the A and B sublattice are opposite, and it is translation invariant. And there are 2 masses which are kind of bond density with a modulation. So this is called K Coulomb mass. So this is really different from what we have in this model, right? And because this appears precisely because the symmetry degrees of freedom are different and the symmetries are implemented differently. So okay, so these were some SU4 invariant phases, but most of the phases breaks this microscopic SU4. One of the examples is this. So consider this mass where this is sigma 4,5 is a generator of SU4. Now this mass doesn't break any lattice symmetries. Oh really? Oh sorry. Okay. So so this doesn't break any lattice symmetries. But it breaks this SU4, and it turns out that if you couple to U1 gauge field, you can find out Chern-Simons and which says that it has some edge modes. I'm not going to the details, but it is a really analog of the spin Hall effect in normal graphene. So in normal graphene, you can break the spin rotation symmetry in, let's say, different ways, and correspondingly, you can have 3 different quantum Hall phase. Similarly, in this case also, I can have 15 different topological phases. And other phases that the 64 I talked about. So other phases are like some density waves, which have either some zigzag pattern or some density wave pattern. But in different, not in charge. For example, there is a density wave pattern when sigma 1,2, where sigma 1,2 is this operator defined in terms of spins. So these are different kind of phases that appear in this model driven by interactions. But the most importantly, there are this new kind of phases that happen that appears in this model, which are partially gapless, which are not present in the case of graphene, whose band structure is kind of this a 2D section of the band structure. So what happens is that in this kind of phases, some of the bands are gapped out, but some of the bands are still gapless. And if you do some symmetry analysis, you can show that this has some density wave kind of same symmetry of a density wave of some spin operator. But these have also some semi-metal behavior. So these are some interesting phases which appears because there is a non-trivial implementation of symmetries and spin orbit coupling is present. And and there are different gapless phases like this, partially gapless, where some of the modes are gapped and some of the gapless. And the phase transition between these two is interesting because even though it happens to gapless points. Okay, but the symmetry protection, if this gaplessness is protected by what symmetry, the STIR analysis, we're doing it is ongoing work. Okay, so yeah, with that, I'll just summarize. So in this model, because of spin orbit coupling, the symmetries are implemented in a non-trivial way. And that shows as a consequence in the different phases that we can have. And because there's an emergent SU8 symmetry in the model, and using this symmetry, you can just, so there's an emergent symmetry. And then because of large symmetry, because you have large symmetry, you can break it in different ways and get different kind of phases. And in this case, there is a non-trivial gapless phase, which are not present in some, let's say, graphene also. So in future, we'd like to study the phase transition between these phases and study some superconducting instabilities. So in this case, we studied what are the different phases by condensing some bilinear of the form chi bar chi. But if you condense bilinears of the form chi chi, like you can have some superconducting instabilities. We'd like to study those. Yeah. So thank you.
Questions? There is that you find, right? So what are the properties? Of course.
Okay, properties means.
Is there anything other?
Okay, so let's say if it comes in a triplet. I've shown just one plot. Let's say some of the gaplesses come in triplets, so 3 in one representation, and if you rotate one, you get to the other. But the gapless degrees of freedom of the 3 gapless modes of the 3 are different. Right? So yeah, so it's really non-trivial in the sense that if you go from one phase to another, different gapless modes are opened up. So while phase transition, it's quite interesting. And if you look at the symmetries, it has. Gapped one closes in the phase transition. Yeah. And yeah, they have some density of kind of symmetry pattern. I mean, if you look at the symmetries, they have some lattice symmetries, they have some density of kind of pattern. They break SU4.
Protected by some symmetries or?
Yeah, it should be protected, but right now we don't know what are the symmetries that protects it. I mean, it's ongoing. We expect it to be protected by some symmetries.
Did that answer your question or no? Okay, so I think we are out of time, so we should thank Basudeb again.